Welcome to this session about C, which will be presented by Olivier Mattelaer.
So what we are going to do today is introductions to C. And the first question is obviously why do you want to learn C? I mean, I typically use this ranking. So this ranking is quite weird. It's basically how much popular a given language is. It's not really how much number of lines of code is written on the language. It's more how much interactions are there online, and in some sense, it gives you also an idea. Will you be able to get feedback on your code that you are written? Do you be able to get help on those codes? So it's quite a weird ranking, but I mean, it's anyway a measure of how much a code is used and how much popular and how much help you can get. So this year we are quite lucky actually, because C is the #1 language for the moment. It's as you can see here on the right, it's quite new. It's a couple of months. But in any case, since basically the last 20 years, C is of course a quite old language. Since basically 20 years, it's always in the top 2. It might have been at some point in the top 3, but anyway, it's a very, very constant language. It's very, which is used quite a lot. Of course, we can ask ourselves what's going on here, and I have actually no clue, and it's not, of course, that important. Also, I mean, to show the strength of C, if we look at the top 5, so the top #1 for the one is C, the second is Java, the third one is Python, the fourth is C++, and the fifth one is C#. You can see that most of them, actually, all but Java, are related in a way or another to C. I mean, Python is basically a wrapper around C to make it much more user-friendly. But of course, C++ and C# are just extension of C. So they are really related to C. So it's not only is the first, but it's also driven a lot of other stuff in still up to now, even with Python. And one other reason why we have lectures only on C is actually because it's also useful for CUDA. So in the past year, actually, we were only one session on C++, and most of the content I was discussing this morning was actually part of the C++ introductions. Now we split them in 2 parts, also because of these new lectures actually on CUDA. So the program of today is quite dense in some sense, and there's a lot of small points. What is how to do a hello world? What is a variable? What is an array? What is a pointer? And so on and so on. So there's a lot to learn, both in terms of syntax. What I mean by that is how to write in practice the name of a variable, so all those kind of stuff, how to start a program, how to end a program. There's a lot of just word to know how to write something which is very C-specific. And there's also a lot of concepts which are less C-specific. You have, if you follow the lectures on Fortran, you will see some concepts overlap quite well with the Fortran concept, and some other are quite new actually. And then, of course, this afternoon we'll build on what we have learned this morning and go to another type of programming, which is object-oriented programming. And then we will focus on the C++ implementations. We use the C++ syntax, but also there what is quite important is to understand the logic behind all those syntax. So let me first start. I guess I will not have in the PDF now. I will not have the animations. So sorry for that. So I think what is always interesting to understand what is a computer first. And a computer is, of course, a lot of transistors. And that's a simple, in principle, I have an animations, but since I changed computer, I lost it. But that's how I learned myself, actually, when I was something like 10 years old, how a transistor works. So you have 2 directions where water can come. You have these big directions for the moment when you see water, and you have this small other one where for the moment there is nothing. And for the moment, in the output, which is the part here, there is no water. But as soon as you put a bit of water here, you have this mechanism that's open the gate, and then suddenly you have a huge flow of water here. And that's what a transistor is. And what is interesting here, that's really binary operations. You have either a current or you don't have a current. Now, moving from that to a computer is, of course, a huge task. And there's a video here that I let for you to look at. It's very interesting. They use they create with domino a small transistor. They create a couple of them together, and they are able to do simple mathematics. Damien, could you mute yourself? Or Thomas, I'm not sure which one of the two is making sound. Thanks a lot. So you can look at that video, and you can see they create a huge domino set for doing a simple additions of numbers with simple transistor. And that's, of course, quite interesting. But in itself, we don't need to know how the transistor work. We don't need to know how we combine those transistors together in order to make a computer, in order to make a sum, in order to make all those stuff. So we don't need to do that. That was quite important for me for years. I think, okay, that sounds too complicated. I don't want to play with those transistors. I don't want to learn how those really work in order to make something. What I want to do is to create a program, to watch a movie, to change PDF, create PDF, download a website or whatever. That's what I'm interested in. I'm not interested to know all those binary details. And the good news, of course, that you don't need to do that, at least up to a given extent. If you play with numbers, you need to know how much numbers are precise, what are the inherent inaccuracy in using binary representations for a float, obviously. But otherwise, you don't need to know all the details. And that's why it's really interesting to use those language of programations like C, is that we'll pass from an abstractions where it's quite simple to play with numbers, actually, not binary number, which is real numbers. And then we convert what we wrote in these abstraction layers to what we call a language machines that can then run on the computer. And the main advantage of C is that by design, actually, this code is what we call quite low level in some sense. So it's quite easy to convert what you will write in C from your language, for what we learn in a couple of minutes, how to write stuff, to a very efficient code machine. So, and that's why we say that C is fast, like we were saying in the previous lectures that Fortran was fast. It's just that by itself, it's very easy to convert the instructions that you write in fast and efficient code. This being said, it doesn't mean that your final code will be very fast. I can give an experience myself. So in the past, we have our code, it's called Mattelaer, it doesn't matter, obviously, was completely written in Fortran. And it was quite okay. And then suddenly we decide, okay, let's rewrite completely in Python. And Python is completely the opposite of Fortran in terms of speed. And Fortran is basically the same as C, but Python is, of course, quite slow. But at the end of the day, our code was 10 times faster, simply because we use better algorithm, actually. So that's very important. Okay, your language is maybe fast, but you need to use efficient algorithm. And Python is very good on that, actually, to provide you easy way to access those algorithms. So always remember, it's not because you heard that, okay, Fortran and C are fast, and they are, but what matters the most is what the code you wrote, and not really the language itself behind. Okay, so we can try with the first example. And since I didn't set up everything, no, I cannot go like that. So we'll go to the terminal. So you have exactly the same tarball on the Indico page. Actually, I was already there. And you have all those examples. And I'm going to use Emac in order to open them. So this is the first example of the lectures. And as all lectures, all those first examples are actually simple Hello World. I mean, the first thing to do is to be able to print something on the screen. So you have a couple of lines. The first line is just an include, and that's saying, oh, I'm going to use a couple of functions, which are in this case standard. This is called std, so that's standard C. And IO, it's for incoming, outgoing, and that's allow you to print something on the screen. So that is telling to the C code, I'm not going to use the huge universe of functions we have predefined for you, but you have to say which one actually you are going to use. In this case, I'm going to use a class of functions, which is defined in that file, stdio.h here. And then you have a couple of comments. So you have two types of comments in C and C++. So you have this single line command which starts with a double slash, and then you can put that everywhere. Then everything after is not interpreted by the code. So that allows you obviously to write whatever you want to make the code more understandable by everyone. And that means in particular by you, because who is the most likely person to read your code again in 5 years from now, 10 years from now, or 20 years from now is obviously you. And it's quite important to try that you give message to yourself to communicate, to tell you, okay, this is what I want to do. This will be annoying. This is what I want to do, and that's how I'm doing it. So you need to pass information, which is useful, obviously, not stupid like this comment, but this is already better, like this print message on the screen. So here at least you have an information, so, okay, what is the purpose of that program? Of course, for that simple program, you typically don't put that much comment, but for large program, it's interesting to comment every function saying what is the purpose of each function, what is the input, what is the output, and what do you expect. So here is the main functions. So everything's, that's still the code, so empty space doesn't matter. And this starts, that's tell, sorry, this pop-ups looks like will come on often. So this will tell the program, this is where your program starts. And this int means your program is going to return a number. So that's a convention in Unix, in convention general actually, that all programs should return a number. And the number should be 0 if everything is fine, and should be 1 or higher number if there is an issue. So returning 0, and then I can return explicitly, the default will be return 0 actually, but I can say it explicitly, return 0, and that means that my code ends correctly. And then finally, the most important line in itself is this one, it's printf, and then the string that you want to pass. In this case, hello world. And /n, if you don't know, it's how you make a line return at the end of the line, actually, so that the next line will be one line below, instead of printing continuously. Okay, so I can quit this. And the next thing I can do is to compile. So one easy way that's worked basically for a lot of language is instead of calling the compiler directly, that you always have issue to remember, I like to use make. So you can do hello make world like this. And then it's going to, since I've put my name with .c, the make programs know how to compile. So in this case, it's going to use cc hello world -o hello world. So hello world will be the executable. So now I can do /hello world. And the program does what I was expecting. That means printing hello world on the screen. Of course, you can call those lines yourself. But make is, of course, a very convenient way to not having to do it. The only thing you need to remember is you don't have to put .c. And the same command will work also for Fortran, for C++, and so on. Okay, let me go back to my presentations. Okay, one thing, so I've done that on my computer. You can obviously do the same things on the cluster, so that's not an issue. The only thing you need to do on the cluster is to, of course, load a module first. And in this case, the typical one to load is module load GCC. I will not try to connect from this laptop to the cluster to show you on Mattelaer 3 or on NIC 4, but I will just write the comment on my terminal. So that would be the line that you would need to use if you connect on Mattelaer 3 or on NIC 4 or any other cluster actually of the CC. Okay. So with that, we can actually start to do real code in itself. So here's a code. I have a young kid which is now starting to count, actually. So I used this example of a table of multiplications just to give you an example. And it is a code which in itself has nothing wrong, but it's of course far than ideal in terms of maintenance and also the time I taken to write that stupid code. In itself, this code is just using the only functions I know so far. I was able to do an hello world, and therefore I just wanted to use that command in order to print on the screen my table of multiplications. So this code in itself has nothing wrong. In itself, you can see that as a movie. This what a movie is doing. It's doing a lot of computations in advance, and then just tell your computer, just print those pixels, and that's it. So all the computations was really done in advance, store in the data, and then print it. But of course, it's not what we want from a code, because now if I want to change anything, if I want not to, the multiplication table of 5, but the number of multiplications of 4, or if I want to have that table of multiplications up to 20, I will need to modify that code in a very heavy way. So that's not what we want. If you want to run that code, you have the link here on the slides. I'm not going to run that one. It's not that interesting, obviously. It's just printing what you expect. So what we want to do is to have a way to parameterize a number. So in this case, we want to replace 5 by a parameter, and I call it I, in this case. And I say that's an integer. So an integer I, and I give its value to 5. In this program, I will not change its value ever. So it's really we can really see it as a parameter. It's not going to be changed, even if I'm allowed technically to change it, and we'll see that later. So now it's a bit better, as you can see, because now if I want to change this number to 4, I have one line to change. So let me go to my terminal. Let's see that, I guess that one, yes, that's the other one, and that's, I don't have it. Yes. So now if I want to change the table of multiplications to 4, I need to do this. And here that's not ideal. I left 5, and I put I. So the interesting point of this printf is also that what it's called print, and F is for formatted. So that allows you to print a line in a formatted way. And in this case, I replaced the number 5 that was hard-coded by this weird syntax, this %d, and that's telling me at this place I will write a digit, an integer. And then I put a comma and I put the integer I want to print. And I use that also for the other lines, but now I have two parameters. I have this one, and now I put twice actually the same parameter. Here, of course, I put 2 times I, 3 times I, and so on and so on and so on, so that I have the correct printout. So now I can compile it. What is also nice with make is that if I'm trying to recompile multiple times the same stuff, make directly realize, oh, you are already done. You have already compiled it. It's up to date, so there is no need to compile it. So that's also quite interesting to use the make functions rather than writing this command explicitly. So now I can, of course, run it, and now I have my table of multiplications of 4. Let me go back to the slide. So one thing I have to stress is that when I'm saying int I equal 5, I'm doing two stuff. The first thing I'm saying, I have a parameter I, which is a variable that I can use later in the code. And the first thing I say, that's an integer. And that's what this int is. I'm saying this is an integer. And then the second thing I'm saying, oh, and that integer, I will have its initial value. You will see that value can actually change during the flow of the code, but at least the initial value will be 5. That's what I'm saying. So I'm giving two informations. I could do that in 2 lines as well. So if I'm going back to my example, I could do in 2 lines and then see I equal 4. One thing I forget to stress, and that's very important, is this semicolon. So every line in C and C++ have to end with a semicolon. So that's really a part of the construct, is that everything needs to finish by a semicolon to say that you have finished your statement. And if you don't put this semicolon, C will merge 2 statements together and typically will not understand and will not compile. So here I put the semicolon, so if I'm doing make, it will compile correctly. If I'm running the code, I will have the same as before. Now I want to let you see what happens if I remove the semicolon. So now I have I equal 4 without the semicolon here. And if I try to compile, there is an error. Actually, it's identify correctly the error in that case, saying, oh, I think you forget a semicolon here. So in this case, it's quite explicit. Sometimes, obviously, you can have error which is less explicit than that, and then you need to understand a bit what's going on. But that's, of course, a very common error that you forget a semicolon at any point in the code. So I will add it for the sake of not having the error next time. Okay, so this is already much better than my original code, but it's still not achieving the full, I would say, goal that I want, is to be able to change both my table of multiplication, but also how many lines I have. So, and for that, we'll use loop. There is multiple type of loop. I'm starting by the while loop, which is not the most used in C. But it's quite interesting to start by that one, actually, in this case. So in this case, I introduce a second variable, which is called j, which is also an integer. And this one, I initialize it to 1. As you can see, for example, here, I put some spaces here. I didn't put space here. That's really up to you. In principle, it's better to be consistent everywhere. And if you're interested, there are always, for all languages, a small manual online saying what is the good practice on how to write code. But in itself, you can basically put space nearly everywhere without any impact, obviously. So you can decide here which one of the two is the most readable. In this case, I prefer this one, to be honest. But you can really decide by yourself. It doesn't matter for the code. So, of course, you need to be very precise in the code you write, but there's a lot of stuff that doesn't matter, and that's typically empty line and empty space. So, yes, so I initialize it to 1, and it is really an initialization because j is going to change during the code. And now I put here conditions saying, do the next line, actually the next 2 lines, the line which is comprised between those 2 curly brackets, do those lines as long as this variable j is smaller than 11. That's a condition that's saying you are going to enter close to the infinite loop, so a loop which can be infinite technically, and when you will hit at any point the value of j which is bigger than 11, bigger or equal to 11, then you will stop and recontinue the rest of the code, which in this case is nothing. Then, of course, when you do that, it's important that the condition at some point becomes false, because otherwise you enter really an infinite loop. And the way we do that in this example is with this line. So this is, of course, not a mathematical line. J equal j plus 1 is, of course, completely wrong in mathematics. Here, the equal is really need to be understood as an assignment. I'm going to assign to j the value which is on the right part of my equality, which is j plus 1. So if j is 1, I'm going to change its value to 2. If it was 2, I'm going to change this value to 3, and so on, and so on, and so on. So now I'm going really to increase this value. Of course, at some point, j will be 11, and this condition will be false, and my program will stop. So I'm going to run the program. So it's actually a slightly different version of the one I put on my slide, but that's really the same idea. I'm making the same mistakes here. Put the I. So I have I, which is the table of multiplications I'm interested in for the moment, and I introduce one more variable, which is stop at, which is saying when I want to stop. Then I'm doing the same print statement as before. I'm initializing j to 1, so j will be my variable that's going to be updating. It's very common to call local temporary variables with single letter, actually, but nothing mandatory, obviously. And then I have my conditions. So instead of j smaller than 11, I have j smaller or equal, in this case, to stop at, so to 10. So that's the same conditions at the end of the day. And then the same print statement with this %d in order to print an integer. And now, of course, I have the three of them, which is variable. So this is I, j, and I times j. And then, of course, the updating of my loop, j equal j plus 1, updating the value of j. So I'm going to compile it. And now I can run it, and oh surprise, I will still have the exact same output as before, so nothing else will change. But now it's already much better in the sense that I can easily change the multiplication, so to 6, and I can easily change what is the limit, the number of lines I'm printing, let's say 23. I recompile my code, and I'm running the code, and now I have much more lines, and now it's not the table of 5, it's the table of 6, which is okay. So that's how it's much better, of course, than the previous code, because if I wanted to print those lines, I would have takes a couple of minutes maybe to write all those lines to check that everything is correct, obviously, and so on and so on. So that's the power actually of those loops and of those variables, obviously. So the next loop is what we call the for loop, and that's one of the most used loop in C and C++, and that's for me, it's one of the key features, a feature that I like a lot in C and C++ is this for loop, which is very nice and neat. So it's in itself exactly the same loop I've done for the while loop, but everything is inside this for part. So now I have everything, instead of having one line, if I go back to here, I say I initialize j to 1, I have my conditions here, when I stop my loop, and then I have my updating, adding 1 to j at each iteration. So now all those lines are combined together in this line number 9 here. I have my initializations. I put j, in this case, I put it to 0, which might be a bit stupid to start at 0 in this case. I have my condition, j smaller than 10. And then I have my conditions again. I could have written j equal j plus 1. I'm using a shortcut j plus plus and saying adding one value to j, which is equivalent to written j equal j plus 1. A very common symbol, I would say, especially in C++, but it's also valid actually in C. And then I'm again having the same print statement. So why I put it actually j equals 0 in this example, I'm not sure I've done that in the tarball actually. It's mainly because in C, it's very common to start to count everything at 0. And that's mainly because array that we'll see later starts actually the first index to 0. So it's quite common to count everything from 0. From this example, to be honest, it's a bit weird to do that. But that's one way to remember me to tell you that, actually. It's quite common in C to count to 0. And that's why it's also quite common in Python, because it's based on C. Actually, from Java, it's also quite common to start to count at 0. And that's only in Fortran that you have seen last week that actually start to count at 1. OK, let me run the code as well. Yes. So here I also start to count at 1 actually, but I put a smaller or equal sign this time, which is equivalent. And then of course, if I compile this, okay, it was already compiled. What do I do? Did I make? Oh, okay. Sorry for that. And now it works. Much better. Yeah, let's continue. Let's check. Yeah, let's do that and then we'll, yeah, let's do 2 slides and then we'll do a small break. So there is actually a third loop. I will not enter into the details because it's not that much interesting. But so there's 3 loops in total. There's this for loop. Always remember also this squared bracket, this curly bracket, sorry. That's saying where your loop starts and where it ends. And that for loop, which contains this weird syntax saying that's my initial value, that's my conditions, and that's how you update your parameter. You have this while, which is very simple. You have to take care yourself on how this condition will change during your code, but you have your while conditions. And you have a slightly different one. It's do code while. So instead of putting the conditions before, you do your conditions after. And that means you will always have this code run once. The first time always go through, and then you quit depending on the conditions at the end. So that's the difference. In this one, your code might never run. If your condition is true the first time, then you will not run that part. This code will be never run. While in this case, it will always be run at least one. And then there is 2 special syntax, which is continue and break, which allow you to change slightly the behavior. So continue allow you to stop what is inside your code and restart to the next iteration. So you reevaluate the conditions, and the condition is still true, you reevaluate the full code again. So that's what the continue is doing, while the break is stopping the loops, and that's it. So you exit the loop. So we'll give some example on that. Okay, so yes, this will be this one. Yeah. So in this one, my point is to add 2 parameters. One is the maximum number of prints. So I want to have at most 8 lines printed on my screen. So that's the point to add this parameter. And I say it's 8. So I don't want to have more than 8 lines printed on my screen. You would say, oh, you can just put this number to 8, which would work if I didn't add also this second, which is called bypass. So here in this case, I want to print all the multiplications table of 5, but I don't want to have the line 5 times 3, 5 times 6, 5 times 9. So all the multiplications of 3, 6 for the multiplicative number of 3, I don't want them to be printed. And therefore, counting the exact number of lines is a bit complicated, so I just want to say print this maximum number of lines. So now, of course, I have to count. I need to remember how much time I've printed my line. So I've added these variables printed that's saying, for the moment, you have printed 0 line. So as soon as I've printed a line, that's what I'm doing here. If I'm printing this, I'm updating printed by 1. So I'm doing printed plus plus, which I remember is the same as printed equal printed plus 1. So that is the same. So now I have those 2 keywords. I will start by this one. If printed is bigger or equal to max print, break. That means go out of this loop, this for loop, and therefore go back here to the code, which is in this case end the code. So that will block the fact that I'm printing more than the number of max print lines, which in this case is 8. I have these other conditions. if j, so this percent is modulo. So if j modulo 3 equals 0, so it means j is a multiple of 3, then in that case continue. That means do not execute these lines. Actually, all those lines will not be executed. And go back to the for loops. It means update j by 1 and check if it's smaller or equal to stop at. So I can compile it. I remember that you have all those functions available on Indico. And you can see, okay, now I need to, you have indeed 5 times 1, 5 times 2. You don't have the 5 times 3 because of this continue. I decide not to print that one. 5 times 4 times 5 times 7. 5 times 6 is also bypass. It's of course a multiple of 3 as well. 5 times 7 times 8. 5 times 9 is also not printed because of this continue. And then after 5 times 11, which is indeed our 8th line, I hit this break statement, and therefore I stop this loop. Not stop the code, actually, it's just the loop. So just to prove that, I can add here a printf statement saying my code is still running, for example. Running, need to close the parenthesis, and always not to forget the semicolon. I can recompile and re-execute. Now you can see that indeed my loop is finished, but my code is still running. And as you can see here, I forget to put a /n at the end. And that's why the printout was not great. So let me add that. Recompile. And that now it's better. I don't have this percent here, which is a bit annoying. Okay. Let me do the next slide, and then we'll do a small break, and then we'll continue in a couple of minutes. So for the moment, I'm only focusing of integer. I mean, that's very simple for demonstrations, obviously. But in practice, you are not going to use integer most of the time. You are typically going to use float or double. I mean, the most common one is actually double precision. And of course, you are going to use string and char. So bool is not native, so you cannot have true false in a really native way. But it's supported actually since quite a while ago. So I expect that all C compiler now should support it. 99 means 1999, but it's also 99 because it's a C99 conventions, which are related, obviously. And therefore, you need to add this symbol, exactly like you're doing here, including stdio that allow you to do a print statement. You can also do include std bool.h that allow you to include this type bool, and therefore you have true, false variables. So how to print, because I think it's always important to know how to print the variables. You have, of course, %d that was for integer. You have %c, and that's for the character. Then you have x, which was a float, a single precision number float is %f, and the double precision is also the same, actually, %f. So let me go to the example variable demo. See. So here I've added, I will put an empty line here. I've added this include stdbool.h that allow me to also have this type bool, and I call it the name of the variable, so I call it check, and I assign directly a value which is true. I have my then for each type, I mean you can run that. It's interesting for you. For each type, you can see how to print them actually. So here I already introduced what is a string. We'll come back to that a bit later because it's quite particular type in C. but you can also see here how to type a string with this %s. Okay. So I think we can take, I would say, 5 minutes of break. Please don't hesitate to ask questions during that time. Damien and Thomas will be able to answer them. I will take to drink a bit, but I will be back also and I will check the chat. So please use that time, I mean, to do whatever you want, but if you don't know what to do, take those examples, play a bit with them, see if you can mess around, if you can change, if you have an idea, play as much as you want. I think it's quite important to practice all those codes. And of course, this format doesn't allow that much of interactions, but on this, do not hesitate to practice. One thing I skip, I think it's quite important. So if you want help on the chat, you can obviously write your code on the cluster and then tell on the chat, oh, here's the code where I have an issue, and then put the path to the file. That's working, obviously. You can also use those websites. So I will copy one. I'm already on the web, obviously. Great. So you have here an editor. You can really edit whatever you want. So I can do this, and then you can execute your code. It will compile it on the fly. You will even see in this case the line it used to compile the code, and then it's executed. In this case, it's the hello world example, and you can use it obviously. But that's allow you as well to create your code there, and then you have a share button here. Then you need to create your account, obviously. But you create your account, you will get a link, and then you can also send us that link. That will allow us to see your code, understand what the issue is, and be able to help you on that. So you can use any of those methods to be able basically to communicate between yourself and between you and I and us to be able to, for us to give you feedback what your issue is, obviously. Okay, so we can restart. So there were questions on the chat about plots. I'm not sure I can look at the Q&A. Deuxième one. Okay, so one of the reasons I'm not using C#, C++, or C, it's like I couldn't find library to plot or to do matricial operations. Do you know what can we do to facilitate this operation? So, okay, Damien, just answer that. Okay, for matricial operations, there are library like BLAST, LAPACK, and something like that. For plotting, he mentions GNU plots. I know also a C implementations of plotting, which is called in root actually. So it's mainly used by physicists because that was developed by the same people. And the root is also not only, well, you can use it as pure C++, but it's also designed as an interpreted language using the same syntax as C++. But you have all the class which are also designed as you can expect. So that's also a solution if you want to do plot in C, C++. But quite often, the typical way is indeed to use external call to something like gnuplot or equivalent. For the moment, I had the code which was quite linear, I would say, so that the code itself was starting in main and going in main and was doing one thing. If you think now that I don't want to print one table of multiplications, but multiple times table of multiplication, sometimes table of multiplication of 4, sometimes table of multiplication of 5, that's where you think that, oh, it would be interesting to make an abstract of that functions and to give them really parameter that can change. And that's what a function is. It's like a mathematical function. That's a function and takes some parameter and then it gives some output. I mean, the output can be nothing, and that's what's the case here. That's saying vote. You see that the syntax is very similar to what is the main function of your code, what is your program, except that you can put different type of output. In this case, you have void, but you could also say I'm going to return a number, I'm going to return a string, I'm going to return a character. That's really up to you. And then, of course, it takes parameter. In this case, this function takes 2 parameters. The first parameter is by which number my table multiplication is about. So it can be 5, it can be 4. And here, what is the maximum number by which will be printed the multiplications. And I'm return nothing because the only thing I'm going to do is to print on the screen. I'm not going to return a number out of it. I'm not return anything actually. So that's why I have this keyword void. But if I want to return an integer, I would replace this void by integer. And then I would need a return statement as I can have in my main code. And then I will return, I don't know, J or something. And for the rest, these lines here are exactly the same as the one we've used before with the same for loop. The only things which is slightly different now is that I have now functions that I can call multiple times, and that's what I'm doing here. I have print table, and then I pass my 2 arguments. So I want to print the multiplications table of 4 up to 10, and the multiplications of 5 up to 11. And that's now, without having to rewrite those lines twice, I will be able to call twice my functions. So one thing which is important is, of course, what we call the scope of a variable. So, to discuss that a bit, let me go to the code. And that's functions. No. What name did I put here? Swap functions. I didn't put this one. Oh, so multiplications table functions. Here it is. Sorry. Okay. So if my print table of. So it's important to realize that I said before that you cannot define twice the same variables. If I put here integer I, and I say float I, the code will not be happy about that because now it suddenly have twice the same name, the same variable name, which correspond to 2 different stuff. One time it's an integer, one time it's a float, and it doesn't know what to do. And therefore, if I'm trying to compile this, it's going to say, no, you cannot do that. You have you say a redefinition of I with a different type, you pass from a float to an int, it doesn't allow me to do that. However, when you have a lot of functions, that would be very difficult to avoid that you have a variable name here, which is completely not, which will never overlap with any other functions. When you have code which 100,000 line of code, and you need to be, if you would need to be sure that no single variables is never used in other part of the code, that would be very difficult. So that's why variables have a scope. So that means they are valid only up to the associates curly bracket. So in this case, what I could do is redefine I here as a float, like this. So this variable I, which is an integer, will only be in the main program of the code. And here I have a second variable with the same name, but it's only valid as a float in actually in this part of the code. So this one. So that's what we call scope of variables, that all variables are actually local to the associate curly bracket. So that's also why in this case, if I try to do a printf of j, oops, sorry. What's going to happen here? Let me remove this line as well. So let's try. So here you would say, oh, you use an undeclared identifier j. So you say that j is not defined. When you look at the code, you see that j is actually defined, but it's defined inside this for loop. So outside of this for loop, this j is not defined. So I can also, outside of these for loops, assign j to something completely different. And that would be okay after at this stage, obviously. But the important point here mainly to understand is that you cannot recover the value of j at the end of the loop. And that's a constraint which is not only always present depending of the code that you use, but that's the case for C and C++. Yeah, so here I spoke about the scope of a variable. A variable has not a value, it's not defined for the whole program, but for blocks in the programs. And that's a concept which is important to understand if my variables can be seen in that part of the code, or if those two parts of the code can be completely uncorrelated variable. And the main rule is that those curly brackets define each of them a scope, and therefore a variable inside a curly bracket is typically not seen outside those curly brackets. So one thing which is also important, so I can define j in this block, but I can also define a table of, obviously. Table of equal 5, and do something like this. So here I put the same name as variable as the name inside the functions. That's perfectly allowed. But I can also put another name. Let's say the name of the variable is not maybe the most interesting one, but okay. I can do this. So in this case, I pass the value 3 to these functions. And that's it. So it doesn't need that this name should match that name. There is no need for that. Here, what we'll take, we'll take the value which is taken in these variables, which is 3, and therefore max and 3 for this block will be associated to the value of 3. One other thing which is important to understand is that you cannot change the variable. So if I'm doing this, I will comment this line. If I'm doing table of equal table of plus 1, what's going to happen? Let's see. So I'm compiling the code. Looks like I forget a semicolon somewhere. Yeah. Running the code now. So you see that indeed the code did what I did. I'm changing the value from 5 to 6, and then what is printed is indeed the value from 5 to 6. Now, what would be interesting, I told you you cannot change the variable. So let's now print the value here, do printf, table of, and I would say like this, table of equal, put the %d to print an integer, and then table of. So I've changed the value inside here. So you see as input type I 5. This line update making table of plus 1. So you are updating the value here. But is this value changed? I mean, to be more clear, it's probably better. Let's change the name. I will put table here, table here, table here, and table here. So that I don't have the same name as table of here. Can recompile, do make. I don't put the /n, but that's okay. You can see that even if inside the functions, the value was spaced from 5 to 6, outside of the function, as soon as they've quit in some sense the functions, you can realize that the value of table was not modified at all. So you cannot change by your functions like this, you cannot change the value of table. I mean, what I put in will always stay like that. So if I put a number 5 inside, whatever I'm doing in these functions, even changing the value, as you see here, the outside, when I go back to the main code, the value will actually be untouched. So that's what we call in programming passing a functions, passing by variable. You pass the value of the of the variable actually. So let's go back to this. Yeah, I'm just checking that I've said everything, but indeed. So in some cases, you want actually to modify a variable. So typically, an example is I mean, a typical math example, you say, oh, here's a list of variables, multiply all of them by 2, or subtract 1 to all of those variables. If you take an array, I have not yet defined what is an array, but take an operation of multiple variables or modify some variables is actually quite common and makes sense. So how to do that in C? And that's where actually I will not answer directly these functions, but that's where address and pointer are very useful. So let me go to describe what is an address and what is a pointer. And that's a quite complex concept. In itself, it's very simple, but as all very simple concepts, they are quite often a bit disturbing when you start with them. So it can be a bit disturbing. It's not very clear what they are at the beginning because you are not used to them. But as soon as you understand them, you understand that it's actually very simple. I always take the comparison with a vector. When you start the first time you have learned about vector a while ago, I guess, this is not that trivial. But now, if you all think what a vector is, yeah, it's something with 3 numbers or more numbers than that. I mean, it's very natural at the end of the day. And pointer address is exactly the same thing. It's actually not easy to understand the first time, but as soon as you understand, it's something which is very simple at the end of the day. So what is an address? So for the moment, we focus a lot of this syntax, which is saying I is a variables, which has an initial value of 5, a value that can change with time, and has a given type, which is an integer. And of course, 5, the initial value need to be an integer as well. So since this value can change with time, the computer has to store somewhere in memory, so in RAM, that variable somewhere. So when the code sees this line, what it's going to do is going to go on RAM and say, okay, on those digits, on those binary number, I will store a number for the variable I, and then I will initialize those 0 and 1 to fit the value 5 to start with, obviously. And that's stored somewhere in your memory. Of course, the code needs to know where in memory he has put that address, and that's important for the code. It's not very important for you, but that's very important for the code to know where that variable is. That's later in the code. As soon as he sees this variable I, he's able to use that address and going to read again what is inside that memory place. But now we have access, we can print. That's the first things we're going to do, is we are able to print where that address is. So yeah, I will not run the example. This is the line of code. You can read it yourself either here or via the tarball. What is going to be printed is I is stored in RAM at address, and then you have one address is of course not human readable. I mean, the point of those addresses is not that you are able to read them. It's mainly for the computer to be able to access them. So there's 2 things which is interesting in this small code. The first one is here, is how to get access to the address, and that is this %I. So this ampersand is saying, I have this variable I, give me the address of I. So that's this ampersand is. And that's, of course, a syntax again, for all those syntax that we have to learn, like integer is called int, equal is for assignment, you have a semicolon at the end of the line, functions with the curly brackets, the parentheses, the name main for the main program. You have a lot of syntax to learn, of course, in a language, and that's one of them. How to get the address of a variable is this A. And if you want to print an address, you have this %P. P is actually for pointer. We'll see later the exact difference between pointer and address. So, okay, so now we are able to get the address. And I'm pretty sure all the people on this feed is asking, okay, but why do we need to know the address? And in itself, it sounds a quite useless concept, I would say, and I would fully agree on that, especially because the place in memory is not predictable. So if anything change a bit, you can try to print multiple times, you can compile multiple times your code, you will see that the address can change. It can also change depending on what you are doing on your computer, technically. So it's not clear what you can do with the address itself. I mean, for the computer, it's clear that it's important for him to know the address. Why is it important for you? And as you will see, that's coming back to what I said before. We need sometimes to change a function, a value of a variable via functions. And in that case, knowing where the address is allow you to say, change the value at that address. And that's why it's very useful. So in consequence, a lot of C functions, but also a lot of C++ functions, and technically also in Python, those addresses are used all the time, even if you don't really realize it, actually. But that's actually a lot of functions will ask you, provide me the address of a variable. So will not ask you, provide me the variables, but will ask you, provide me the address of the variables. And that's why addresses are very useful, because sometimes functions will need them. So if you can access, and if sometimes we ask you the address of the variables, one question you can ask yourself, even I'm pretty sure you say, I'm not sure still why I need to use address, but don't worry, this will come. The next step is, can I store the address in another variables? So can I have two variables? One variable, which is my normal variables, which contains an integer, 5, 6, 7, and one, in this case, I call it pi, which contains the address of that variable. So whatever it's this crazy number that was printed on the screen on the last slide. So actually not on here. So that's a variable that contains this number. And that you can do in C. And of course, since everything is strongly typed, you have to have a specific type for each address. So in this case, it's an address of an integer. So that will be named int star, the star saying, this is not an integer number that I'm storing, it's an address of an integer. And that's important that each type of variable, so an integer, a double, a bool, for example, doesn't have the same size in memory. So of course, it's not important only to know the first bin, the first binary number where we store the value of an integer, we store the value of a float. It's also important to know the number of binary number. And that's why we have different type of pointer for different type of class, integer, float, character, strings, and so on. So that's why they all have their own class, and therefore they all have this easy syntax, actually. You add a star. So an integer is int, a pointer of an integer is in star. A float, a variable float will be float, the pointer to a float will be float star. A bool, the same, character, the same, and so on, and so on, and so on. So that's what it is. An address is where it's stored in memory. The pointer is a variable which keep this address as a variable. So you can access, you can change it if you want. It's not that useful, but and so on and so on. So there's also an operator, and with again this star. That's where sometimes it starts to be a bit confusing. So for the one we've seen the star for the class definitions. So if int star, so it's a pointer of an integer. So pi will be a pointer of an integer. In %i, that means I is the variable, and you take the address and you feed the address of I inside this pointer. That fully makes sense. Now, if you have a pointer, pi, you can say, can I have my value back? So what is, that's what this syntax means, what is the value stored at this place in memory? And the syntax for that is star, and then the name of the pointer where you want to look what is the variable is in memory. So pi is an address, and I'm looking at that address, see what value is. It's like you have a couple of houses, you have an address of a house, and these operations will look like which people is in that house, which is a bit different than the variable itself, where we look at the person itself. So I will basically re-say the same things a second time with a slightly different slide, just to try to be sure that you understand the concept. So a pointer is a position in memory of a given variable, and a pointer is a variable itself. So here I have a representation. So that's what I represent by my memory. So if my memory is a lot of positions, like a map, and then here that's my position in memory, I have an index 1175, 1776, 1777, and I have all those numbers up to 30 gigabytes of RAM technically, or 64 depending on your computer. And then I have a variables myvar, which contains a value, in this case it's 25, which is stored in RAM at that position, 1776. So if I take this foo equal a myvar, so this ampersand, that I take the address. So now I have a second variable, which is named foo, somewhere else in my memory, which will contains now the value 1776, which is the address here of the variable myvar. So if I'm doing, on the contrary, simply another variable's bar equal myvar, I will put somewhere else in memory another variable's named bar, which simply contains 25. So if I'm doing this or this, the content of these new variables is of course quite different. So I can continue here. So if I'm doing foo equal a myvar, so in this case, I have foo equal 1776, exactly like here, so it's the continuations. So now I can difference, so I can do base equals star.foo. So that means let's look at the positions 1776. In these positions, there is a variable's value 25, and then in base, I will assign that value, which is 25. So this is really the opposite operations. The A operations taking a variables give the address, the star operator take the address and give the associated value. Yeah, and that's we already said. So due to the fact that we need to be able to revert the operations, so we need to go from a variables to an address to other variables. That's why actually it's very important that each pointer has its own type, and that's why the type is the name of the variables and then a star. Okay, so now I can go back to my original questions. What if I want to change a variable via functions? And what you can do, so here I put an example named swap. So the idea, you have two integers and you want to swap the value. So you have the first integer, so in my main code here, a equal 100, b equal 200, and now you want to swap them. And that means in a, you want now the value 200, and in b, the value 100. So you want the functions that actually change what is inside of your variables. That's the point, of course, of this exercise. And for that, what you're actually going to do is to not pass the variables, because you cannot modify your variables. What you are going to provide is the address. And then in your code, you are going to say, write in this address this other value. And that's what we are going to do here. And I'm going to go to the terminal to do that. Okay, so this is exactly the same code as before. One thing, well, I will mention that after. So I have here my function swap. I create a variable, so this is a normal variable, so a temporary variable, so I call it temp. And inside temp, I pass I put the value associated to the address of x. So here I conveniently call px the address of x, and y in some sense the address of y. I started by p to say it's a pointer. So you can see here my function takes two arguments, which is, I call it like this, which is a bit more readable, which is the same, which is a pointer of an integer, which is called px, a pointer of an integer, which is called py. So on the back of my mind, you can see x and y associated to them. This I think is comment. So now in top, I'm looking at the address of px. I say that is the value of my first variable. So my first variable is a, was 100. So now in top, I will have 100 inside. So now I'm using this syntax. I'm saying at the place of px, put the value of py. So in some sense, this is saying change at that place in memory, at the place of px in memory, and now instead of having whatever value, put the value stored in py. The value stored in py that corresponds to the b, so that was 200. So I put now at the place where px, which means the variable a, was stored in memory. Now instead of having the number 100 written, write the number 200. And then we do the same now here for the second address, which is a place in memory. Replace what was at that address by this value, the value that we have stored just before, which is 100. So in those lines, I will comment it later. So I can compile the code and run that code, that's better. And then you see before swap, the value was 100 for A and 200 for B. And after the swap, the value of A is now 200 and the value of B is now 100. So indeed, they've swapped to each other. Yeah. So that's how you change variables inside the functions. And for me, this syntax is quite clear because what you pass in the functions is not the variables, but the address. So the address will not change, but what is inside, what is at that address can change. And then it's quite clear if when you pass an address to a function, it's quite clear that you allow the code to change what is at that address. So what you can do as well, obviously, is to print this, and that's quite interesting. So I'm now going to define two integers, x and y, and I'm saying x is the value stored in px and y is the value stored in py. So I can do, and that's the first thing to do, is to do printf. X is, and I will print this value, and y is, I will print this value, x, y. So in this case, that will print me the flipped value because I'm making the flipping first. Then one thing which is interesting is I'm printing the address of x, and is it the same as the initial address here? And that's what that's confused a lot of people. That's why I want to print it. Yes. Let me make this a bit more readable with /n. Okay, that's much better. So in this case, indeed, x and y are what I expect. Those lines were after the swap. So indeed, they correspond to the same value of a and b in my main program. But you can see, and that is quite important to realize, that x has an address, which is this one, which is unreadable, obviously. But the address I pass in the functions is actually this one. So when I'm doing those lines, I'm really redefining a new variable x, which has the same value as the original one, but actually has its own address. So I cannot do this, saying, okay, and then changing x. So if I'm doing now, what do I do? If I'm doing x equal y, I will change the value of x, yes, but I will not change the value of a, because those are actually two different variables, this one and this one. So that's what I wanted to stress. So that's why you really need to have this syntax here to say, so this is really the way to say modify at that place in memory. And I can compile that. So you will see that in this case, since I put x equal y, I mean, if that was working, that naive idea would be working, you will have both at 100, which is not the case. So that's indeed because these x variables is not the same as my a variables. They have two different addresses when I'm doing that. Okay. Let's continue. Okay, this is nothing interesting. We already have made a lot of if statements, so I will not pass too much time on this. One thing which is interesting in C, and that's why I put this slide, is actually this one-liner, this ternary operator, as it's called, to have the correct name, saying you have a conditions, then you have a point mark, then you have what is going to be assigned if it's the true, and that's what is assigned to be if it's the false. So that's a very convenient shortcut in mathematical computations to sometimes, rather than having those huge constructs that takes a couple of lines, it's sometimes quite practical to have this construct actually. Okay, there is more syntax and definitions. If you have if statement, one thing which is of course quite interesting is to have this AND OR operations, this logical AND, this logical OR, and you have those syntax which are a bit obscure to my point of view. You have other code with much better syntax to my point of view, but they are quite common. So the double A for the logical AND, the double vertical bar for the OR, the point mark for the NOT, and so on and so on. So now we can go back to another class which is very common, which is an array. So in this case, what we want to do is to represent a list of numbers. So this is of course quite common, very common actually, to have a list of numbers, to have a list of characters, to have a list of whatever you want. That's one of the basic objects, I would say, in programming, and to have an array. So in this C, the syntax is you add a curly bracket, and then you have two choices. In this case, you specify, you initialize directly what is the list with this curly bracket again, and you put all the value. And then in that case, you will infer directly, okay, this array is size 1, 2, 3, 4, 5. So that's very simple for him. And then you don't have to specify it. If you don't put an initial value, you are forced to say what is the size. So in this case, I'm saying I have n with an array. So it's contains 10 integer, but you are forced to put n. You are forced to put a 10 because otherwise the compiler doesn't know how much memory it needs to assign. So that's what we call static allocation. We'll see later, or we can do that in a more dynamical way. But that's the most basic type of allocations. Is saying I want to have a given number of integer. I want to get a given number of char, a given number of float, and so on and so on and so on. And then you have this square bracket, and you put the number of argument that you want. So one thing which is important to realize is that in C, and that's can be a bit counterintuitive at the beginning. In C, the first element is the element 0. So we have element 0, that's element 1, that's element 2, that's element 3, that's element 4. So when I do an assignment saying balance equal balance 4 equal 50, what I'm going to put is I'm going to modify the element which is 4 for C, which means it's the 5th element. And it's actually, I mean, it's disturbing at the beginning. Really, we say, oh, I'm modifying the 5th element, so I need to put 5 minus 1, it's 4. And it can be a bit confusing, of course, at the beginning. But in the long run, it's helped quite a lot. You have a lot of cases where if you start at 1, it's going to hurt you in terms of the conditions that you're going to put, and a lot of stuff will be a bit weird actually if you start to count at 1. So that's why everything here starts to count at 0. So when you do an assignment, you need to make a bit that gymnastic, but in the long run, it's much, much easier. And that's why one reason is all the conditions here smaller than 10 start at. It's very convenient at the end of the day. All the conditions for the start and end. That's why actually we do that. So in this case, so I have created a list of integer, an array, that's the exact term, of 10 integer, which they are not initialized, so they have random value. Depending on the compiler, they can all set them to 0, or you just put random number. It's really dependent on the compiler. You cannot really rely on that, except if you put some compilation flag on those. And then I'm going to initialize them one by one. So I'm going to initialize first the I equals 0, so this first element. In this case, I put I plus 100, so that means this one will be 100, the next one 101, and so on. And then I'm going to print them, and there is no simple way, I would say, to print an array. What you can do, what you have to do is kind of a loop over the and make a printf with a loop. So in this case, I'm making a loop over j. I could have put I again, actually. And then I'm printing my element. So let me go to the code. And this is exactly the code I've showed to you. So here I'm creating an array of 10 integer, not initialized. I'm initializing them here with this for loop, putting value from 100 to 109. And then I'm going to print those values. So now if I'm doing make array, and I'm running it, why make array? Okay. Looks like I've compiled on my I've compiled on my other computer, and therefore I need to recompile. I need to force recompilations on this one. So that's why it was crashing here with this. Where was it? Yeah, this exec format error. That's because the binary is not compatible with this laptop. Now it printed them from 100 to 109. So let me look at the next file. Okay, so it is a small code which is not doing that much. So I define an array, which is 5 components, 6 components actually, sorry. And then I'm going to print the pointer of the first variables, so of this one, and to print the pointer of the full array. So I'm going to say it again. So this is the ampersand my array. So as if you remember, ampersands give you the address of a given variable. So here I take the address of the variable my array, and here I will put parentheses to make it even more clear. Here I'm taking the first entry of the array, and I'm taking the address. So I'm going to compile, and then I'm going to execute. And the interesting point here is to realize that actually this address and this address are actually the same address. So they're actually going to point on the same place in memory. So when you pass an array, what you actually pass is the pointer to the first element. And that is quite interesting, because then when you pass it to functions, you can use that. So I will go back to the slide. So in this case, I have two functions. One is expecting a pointer to an array, and one is expecting actually an array. And you can see after the code is actually exactly the same. I'm just taking my array I. So array are actually pointer. Those two codes are completely identical. You can access a pointer, you can access an array in the same way. Bracket 0 means it's the first element, where it's store, plus 1. So bracket 1 means you are access the second element of the array, and so on and so on. So that's also allow you to do this. So if I'm looking at those functions, average, I can also saying, oh, I want to have the average from not my whole array, but only a part of my array. And then what I'm doing, if I want the average of the last 5 elements of an array of 10, I put 5 here to say that's my size, that's the number of elements on which I want to average. And then I pass the first element on which I want to average. And to pass the first element, I'm saying taking the fifth, which is the first element I want to pass, and then say I want the address of it. And therefore, that's for the code, it's like if you pass an array of 5 elements starting from element 5 to 10. 5 to 9, technically. So let's go that and run the code. Not sure I have it that one actually. Yes, I do. Okay, so this is a function's average, which in this case I say I'm taking a pointer, but I could completely say that I'm taking an array. That's exactly equivalent. So I'm only doing one or the other, but it's technically the same. In this case, it makes a bit more sense to say I'm passing an array because I'm using it as an array. And then size is how much element I would average. Then I'm taking a float, and then this for loop. I'm printing all my elements. I'm adding my average value, and if I want to be secure, it's better to initialize it to not have surprise with the compiler. And I'm going to plus equal means I'm going to update the value of average and adding the value of that element of the array. And then, of course, I'm going to divide by the size to get the average, and I'm returning the average. I don't think I did that much functions at returning something, and that's one example here. And here the main code is the initializations of the array as before, then printing the element as before. It's already printed here, actually. So I will not do it again. And then I'm just printing the average. So let's compile this. What did I do? Okay, so they make an error. I put a %f somewhere where it's but that should be, what do we have? This average is, why do we have an address here? Yeah, I'm not sure what I tried to print it before, but let's print this average is, and then I put the average. That should be okay. Sorry for that. Yeah, now it's compiled. And so I have taken 5 elements and average is 107, and that's exactly what I described before, right? I'm not taking the average over my full array, but I'm taking the average over the 5 last elements of my array. So as a side note, one thing that you can do is to do this. So instead of, here I've always defined so far the functions before the main code. But what you can do, and that's important for the ordering actually, if I'm doing this, so let's remove this and put it here. So the ordering is actually important, and as you will see, if I'm trying to do that, so if I define my functions after my main code, it's not going to be happy again. And basically, okay, the error is a bit cryptic, I would say. But the main issue is that it doesn't know what to do with average. Implicit declaration of function average is invalid. It doesn't know what average is. So what you can do, looks like it will be valid later in C. That's interesting. What you have to do, if you want to put the definitions after, actually the only things that the code needs is that before in the code we have this what we call signature. So we put float average, and in this case I put int star, saying it's a pointer, it's an address, which is the same as an array, and then int. So this is what we call the signature, saying to the code, here you will pass an address. Address is the same as pointer, and then you'll pass an integer, which is the size on which you are interested. If you do that, then the code will compile correctly, because now, before reaching the line where it needs to call average, it knows at least what it has to do, and later it will be defined, so the compiler will be happy. So now if I'm doing make, everything's compiled correctly, even if my definitions of my code is after the main functions. And that's also why, and we'll going to come back later to that. That's also why you quite often see in C and C++ some .h file and then some C file. And the .h file typically contains all those lines actually. And then you do simply an include here in order to have all those definitions where there's only signatures and not really code that you typically put in the .h file that's define all the functions that you define actually. But that's so that you will often quite see in C and C++ some .h and .c for C and .h and .cpp for C++, and that's simply this header in some sense where you announce what you are going to define so that everything is defined in advance and you don't have issue of ordering basically. It's sometimes mandatory when you have functions A that call the functions B and the functions B that call the functions A, then you have kind of infinite loop, right? It's impossible to define first A and then B because you always have to have the other one defined. So with those signatures, that's not an issue. Okay, that was the discussions. Okay. So now I can come back, I mentioned it at some point actually, to the strings. So there is no native strings type. There's a couple of functions that are able to be handle strings that can be included if you do include string.h, but in itself there is not a type like an integer, like a float, like a character, which is really a strings in C. So the way to represent strings in C is simply an array of character. So that's why if you want to describe a string, you do char, you say it's character, but you say it's an array of character, and then you can define it actually with this simple double quote. So there's a difference in C between single quote, and that's for a single character, and double quote would be for an array of character. So you can define it as double. So some other language, for example, Python, single and double quotes, there's no difference in Python. But in C and C++, it's a single quote and a double quote are completely different. So behind the scene, actually, there's a small character /o, or no /0, actually, sorry, which is telling, oh, my string is stopping. So there's a special character for the code that you actually, when you write this, what is written behind the scene is actually this. So you have an hidden character /0 that's telling that your strings is ending actually, which is quite kind of important, obviously. And then you have a couple of functions on the strings, like copy string 2 into string 1. As I said, you need to put this include with the hash, actually, I forget the hash. Include string h. You can concatenate string, and you can get the length of the string, which is the typical operations on string. Okay. No, I'm not going to make a small break here. We are close to the end, actually. We have still 2 topics to cover. Maybe I can just check if there's questions I need to ask on. So can we create, that's I think interesting for everyone, can we create a list that contains different type of variables? No, no, that's not possible in C. That's possible in Python, but that's not possible in C. And okay, so data structure. So for the moment, what you have seen is different types of data, which was the integer, the float, the character, the array, which is also data, and that's basically it. So it's quite limited what you can do. What we have to extend that is what we call data structure in C. So data structure is now, you have a set of parameters with different attributes. I mean, for example, let me do what I'm doing here. So it's a formations. We have some information about the number of students. If I look here, I can say that for the moment, there is no one. That's probably a bug, but okay. So there are a couple of people attending, even if my team say there is no one for the moment, that something's buggy. You can say the name of the formations, which is C programming in this case, and the name of my name, which is Olivier Mattelaer. And then you can define the structure, which is saying, okay, that's my data, which is not anymore a single number or list of number. It's now really multiple attributes. So you have what you call, this is structure formations. It has a title, which is C programming, as a speaker, which is my name, and an integer. So those are two strings technically, which up to size 50. And then an integer to say the number of students. And I can add additional informations. And then I can define more than one. So in this case, I have my formations for C. I have my formations for C++. And I can define both of them, initialize both of them independently. And then I have my two data structures. So let's go back to my terminal. Data structure.c. So here I've only initialized, so I'm defining my structure here, formations with three, what we call attributes, title, speaker, and number of students. And here I'm initializing, so here I'm initializing two formations, one formation for C and one formation for C++. I have already initialized the one for C++. So the code say I'm alone. It's certainly not true, but just for the fun, let's keep 0. And here I'm going to initialize the one of C++ and put the title C++ programming, C++, yes, and the number of students I will keep 10, but I need to say it's plus plus, yeah. So one thing which is, again, a syntax is how to get access to a given attribute is by this dot. So dot is saying I'm looking the title of these data structures, lecture C++. Why this title dot is the data structure is the attribute of the lecture of C in the title. So here I'm assigning them, but then I can also make this print statement, and I will add the same print statement for C++. So formations given by a student, and now I'm just putting C++. And this I will cover later. So I'll comment here. So I will compile this, and then I will run it. And then I'm printing my two stuff. So it's a very easy way to organize your data in a consistent way, to have those blocks of data, which is the data structures. Obviously, what you can also do, and that's already in this file, actually, you can also have functions. So in this I'm adding the function print stats, which takes a structure, and that you are forced to specify that it's a structure. The structure, which has the type of the structure formations, which is defined here, and that's the name of the variables. Exactly like before you were writing in for other functions, void fct name, you were doing this at x, at was an integer and x was the name of the variables. So now we have formations, which is replacing int, but we have to specify on top of that that it's a structure. And then what replaces x, in this case is a name, and I put my formations. But here you can really put whatever you want. Like form, for example, which is not very clear in that case. That's why I put my formations, let's say my form, to change. And then I do my form. Number of person, let's remove the typo, in this formation is, and I put that number. That's an easy way to get access to all those attributes. So now I can recompile. Did I? No, if I want, this would never compile, obviously. That's for the example. And now I can add the call to that functions. So make data structure, and now I can run data structure. And now I have this line plus number of persons in this formation. I could also put, of course, access to the name of the formations is 0. So here we'll continue a bit. You can pass, of course, the what we call by value again. You can also say, oh, I want to pass the address now, so that I can change the formations. So what I will do another function which double the number of students. So what I would do now, and that's now I have a pointer. Unfortunately, you cannot do this. For pointer, you cannot do this. This will not work. What you can do is this, my form title. So I'm going to change what is at that address. And I'm doing 2 times the value my form title. The semicolon, and I don't need this print in this case, and I don't need to return anything. So now I will call these functions in my main code. Do one student, and I'm going to reprint those lines. And compile. Yes, obviously. So here, this function accepts a pointer. What I give it to him is the variable itself. So that's why it's crashed. I need to pass the address. To get the address, I need to add this ampersand here. That should work. That should work. What do I do? Oh, okay, yes. That's stupid of me. I want to double the student. I don't want to make 2 times the title. So here it's NB student. Sorry for that. That's what we call the demo effect, right? You are not focusing enough on what you are doing because of the demonstrations. It doesn't like that. This should not. Okay, here I'm confused myself. Yeah, no, this should be okay. Yes, obviously I put 0 students, so making times 2, it's not very worth it. But okay, let's continue. So you can have pointer, and that's what you see also here, and know the special syntax to access the attributes. So that's the arrow, like here, to get access to them. That's an important point. Okay, so now to finish, actually, a last topic, which is dynamical memory. So in practice, having to know in advance the size of your vector can be annoying, and that multiple cases. I mean, it can be annoying because first you don't know before runtime how much data you need, because that's an input of the size to allocate a size, which is typically too large because you don't know in advance how much times you need. Therefore, it's important to be able to have a dynamical memory. Another reason why it's useful is if, for example, you need to have a lot of memory. But it's pointless to have the compiler to assign all those memory at the beginning. It's better to really have that dynamical memory done on the flight. And that's why dynamical memory is also better in that sense. So what we do, the first things we do, we initialize a pointer of an integer in that case, and we say it's a size 3, and then we get back actually the vector, the pointer, sorry, and we assign with these functions malloc, we assign actually 3 integers. So we say I have an array technically, which will be size 3, and that's how you get it. You say the malloc in saying, tell the code, create me on RAM a size 3 of memory. So that's, of course, at runtime. So it has a cost because you do that at runtime. You also need to be careful on that if you doing always that and never free those memory, then the memory will start to blow up. And that's what we call memory leak. And that's important that you manage, when you start to use dynamical memory, that you start to manage memory carefully. That means, if you put an infinite loop, I mean, a big loop, and that you always only create new memory, then at some point you'll have a problem. So here is one example. So you start exactly by this, by starting saying, I want to have my vector of size 3, but it's important that now you don't tell the compiler actually to put a vector 3 like before, like we were using an array with this bracket 3. Now it's really at runtime that you assign this vector. So since it's also at runtime, there is no assurance that you will be able to get that memory. I mean, when you ask for that small amount of memory, obviously there is no issue, and it's quite unlikely that the code will not get enough memory. But if you ask a large number of memory on a system which does not have that much available, it's possible that the malloc call, so the fact that you're going to ask the RAM to allocate you memory, will actually fail. And in that case, the pointer that is returned is the vector null. And therefore, you can and you have technically to check, if you want to be consistent, that your vector is null, that you don't have that memory available. And typically what you do in that case, you return, and since this is an error, you return 1. So that's here actually an assignment of a size 3 vector. Typically, of course, you don't have size 3. Size will be a number that will be guessed or computed on the flight in those cases. But yeah, it's a variable, so it can change. Then I have my array technically. A pointer, as you remember, a pointer is an array. So I can now assign all my member, the first element, the second element, and the third element. Remember that vector, that array, sorry, start to count at 0. And then what you can also do is to reallocate. So to reallocate is, in this case, what I want to do is to pass from an array of size 3 to an array of size 4. And that's why it's size plus 1. And then if this condition is true, which is not the case for the moment, and then I'm going to reallocate, and now I'm doing size of, I'm not sure why this is char, this should be int, sorry for that, because otherwise it's not consistent, obviously. And then I can assign that one. Then I can print the size, print the value of my array, and so on. And of course, what is important is then when I'm done with that array, I need to free it. I have to say to the code, okay, that memory is not used anymore, and therefore you can trash it and you can make it available for me later in the program or for someone else. And that's of course very important, because if you don't do that, your memory is going to explode. So in the main code, to be honest, here it doesn't matter, because anyway the code is going to finish, and therefore everything will be to free. But it's important to always keep them, and you will typically have warnings at the compiler if you don't do that, because in that case, if you want to change your main in a function and you didn't include them, then in functions you forget to include them as well, and that will start to create problems. So always free all your memory that you assign dynamically. So that's a bit the burden, I would say, of dynamical library, of dynamical memory, is that you will need to tackle it yourself. Okay, so my conclusions here is mainly that coding is something that you have to learn by exercise and explorations. I mean, we didn't have time, especially this format doesn't really fit very well. I will try a bit this afternoon actually to give you really time to make exercise and really try to have feedback. But of course, this mode of lectures online is not the most adapted for it. But I really think that in a way to code, in a way to learn a code, what you have to do is to do a lot of exercise. So take all the exercise I've shown to you today and try say, oh, if I'm now changing these functions and I'm doing something I cannot do technically, what will happen? Is that make sense? And that I think it's really important, to learn the language in order to understand all the corner cases which are slightly different from a language to another. I think it's really exercise is the way to learn those concepts. You will not learn exactly what is a pointer if you only listen to me or listen to people. You need to use them to try to understand them as much as possible. My other conclusion is, of course, C is really a language that is used a lot, and therefore having a good knowledge of C is very crucial if you want to understand deeply what is Python, if you want to understand what is C++, what is C#, and those two is really mandatory. But even in Python, having a better understanding of key, I think, is important. And at the end of the day, there's really two types of stuff. You need to understand the abstractions, what is the logic. For example, it's clear for a pointer, what is the logic behind the pointer, but also what is the syntax, and that is nothing really interesting. Oh, and otherwise you need to use the ampersand. If you want to take the address and take the value associated, you have to have the star. I mean, those are not that much logic. If you have an if statement, you have after to have a curly bracket, then you need to close your curly bracket. Those are all a lot of syntax that you need to be used to, obviously, but that you need to learn also, and then the best way to learn them is to write code, obviously.